Alright, so we're going to continue on looking at our exponential functions unit here by specifically looking at how to solve exponential equations. Now, solved a lot of equations of different kinds, linear equations, quadratic equations, so on and so forth. Now we're going to look at exponential equations, specifically ones where now the unknown is going to be inside the exponent. Okay, before getting into that, just remember that just looking at some types of equations we've seen before, remember that when our equations are balanced, we can make certain conclusions. So, for example, you look at A. If we have 3x minus 5 over 7 and x minus 9 over 7, well, since both sides of the equation are divided by 7, you could easily multiply both sides of the equation by 7 and get a conclusion that 3x minus 5 equals x minus 9. So if you're looking to solve an equation like this, that would probably be the first step you would do is, again, multiply both sides by 7 to get some more simplified form. If you look at B, if you have 5 divided by x squared plus 4x and 5 divided by 9, well, since both sides of the equation are completely underneath 5, both in the denominator there, you can conclude that x squared plus 4x equals 9. Okay, and we can continue on along the same vein. So we have the left side of this equation is completely squared. 3x minus 8 over 4 all squared equals x plus 6 all squared. Well, square root of both sides would tell us then that 3x minus 8 over 4 equals x plus 6. And last but not least, and this one would be an example of an exponential equation here where you have your variable or your unknown in the exponent. If we have both sides under a single power, so here we have 2 to the x and 2 to the 2x minus 3, both sides have a single power, they're both under a base of 2, so you can say the exponents are equal. X equals 2x minus 3. And that's going to be the key that we're looking at here. So you'll notice here that we had both sides of the equation under a single power, all with the same base. Okay, and then at that point we could say the exponents are equal to each other. X equals 2x minus 3. Okay, so let's remember that. That's going to come in a lot useful in later. So let's just think about this last one graphically. So remember, we started off with 2 to the x equals 2 to the 2x minus 3. We want to check to make sure that this actually gives us the same result as solving the equation x equals 2x minus 3. Okay, so we can try to plot these on the graph here, but I did it on Desmos here, it looks a little bit nicer. So if I take y equals 2 to the x and y equals 2 to the 2x minus 3, the two equations we had there, and I plot them, you'll see they intersect at the point 3, 8. But most importantly, the solution, the x value of this equation is 3. Okay, so the equivalent equation I got by taking the two exponents and saying them equal to each other, so x equals 2x minus 3, let's see where those two lines intersect. So if I put y equals x and y equals 2x minus 3, you'll see they both intersect at the point 3, 3. And the most important thing you'll see here is that the x value, the one we're solving for, of both of these equations is the same. Both of these equations, both these points of intersections are at x equals 3. So whether we solve the equation 2 to the x equals 2 to the 2x minus 3 or x equals 2x minus 3, you get the exact same x value. And the second one right here, with the exponents set equal to each other, x equals 2x minus 3, is much, much easier to solve. Okay, you could solve this one quickly, very, very quickly, by going subtracting the 2x from both sides. You have x minus 2x equals negative 3. So you get negative x equals negative 3, or x equals 3. Okay, and this is much, much easier to solve. So whenever you're solving any kind of an exponential equation, as long as you have both sides of the equation under a single power with the same base, you can set the exponents equal to each other. So that'll be a strategy that we're going to have as we go through a lot of these problems. Okay, so, and again, just to remind yourself here in your notes, you can only equate the exponents if each side of your equation is expressed as a single power of the same base. If you can't do that, then you can't equate the exponents, and all the stuff that we just did is not possible. Okay, so again, both sides of the equation, single power of the same base. Okay, so in the whole idea of trying to express things as a single power, this isn't an equation here, but I just want us to get used to the whole idea of trying to express an entire expression as a single power, because that's going to be absolutely vital to try and solve these problems. So if you look here, none of these powers, none of them at all have the exact same base. We're trying to express them all as a single power, which means it should be possible that all of these numbers, so 16, 64, 1 over 5, 12, 32, and 128, should all be expressed with the same base. Now, way back when we started looking at exponent laws, I told you to recognize certain powers because it would be helpful to rewrite them under different bases. This is where all that comes in. So you should be able to recognize by now that 16, 64, 512, 32, and 128 are all powers of 2. Okay, so I can rewrite all these bases as powers of 2. I'm going to do that step by step and see what we get. So I'm going to rewrite 16. So 16 is 2 to the exponent 4. Okay, 64 is 2 to the exponent 6. Okay, now 512, I know it's 1 over 512, I'll deal with the 1 over part in a sec. 512 is equal to 2 to the exponent 9. Okay, so 1 over 512 would be equal to 2 to the exponent negative 9. So remember, if we want to change the exponent from being positive to negative, we take the reciprocal of the base. So if our base here is 1 over 512, we could change it to a base of just 512, but have a negative exponent. So I'm going to rewrite that guy as 2 to the exponent negative 9. Okay, let's keep going. In the denominator here, I have 32. 32 is 2 to the exponent 5. Okay, and last but not least, 128 is 2 to the 7th. And that cube root, if you remember your rational exponents, means it's to the exponent of 1 over 3. Okay, so what I've done is I've rewritten all of these different bases, all as a power of 2. Now, I still haven't simplified it all to one single power, but at least I have everything under the same base, so I can start using some exponent laws once I simplify. So the first thing I got to do, of course, is I have, in all these situations, I have power of a power, so I need to multiply these exponents. I'm going to do that next. So I have here 2 to the exponent of 4 times negative 5 plus x. So distribute the 4 through here. So I have 4 times negative 5 is negative 20. 4 times x is 4x, so negative 20 plus 4x. Okay, so then I'm going to have, with the red one here, so 2 to the exponent 6 times 2x minus 6. So 6 multiplies by 2x and by minus 6. So I wind up with 2 to the 12x minus 36. Okay, and for the black one here, again, negative 9 times 4x plus 2 gives me negative 36x minus 18. Okay, down here I have 2 to the 15x minus 5. And then I have 2 to the 7 over 3. Okay, so simplified it a little bit. Still have a long ways to go here. So I'm multiplying all these powers together, so I need to add the exponents together. Okay, so I'll work the numerator and the denominator separately. So putting all these together, I'm going to get 2, and I wind up with negative 20 plus 4x plus 12x minus 36 plus negative 36x minus 18. So I'll do that off to the side here just so to save myself some space here. Again, I'm just adding all these exponents together. Okay, and you have to collect all your like terms and simplify here. Okay, so I wind up with 2 to the exponent of negative 20x minus 74. Okay, that's my whole numerator. Okay, so for my denominator, I'm going to wind up with 2 to the 15x minus 5 plus 7 over 3. Again, just adding the exponents there in the denominator. So I'm going to wind up with 15x, and then negative 5 plus 7 thirds is negative 8 over 3. Okay, so again, it looks kind of complicated, but again, it's the same ideas we've done before, just with more complicated expressions here. So last thing I'm going to do, I'm dividing these powers of 2. Bases are the same, I'm going to subtract the exponents. So I'm going to wind up with 2. I'm going to have negative 20x minus 74. I'm going to be subtracting the exponent that I have in the denominator, so 15x minus 8 over 3. Okay, and at that point, some quick math, or relatively quick math, should tell us that we're going to have 2 to the negative 35x, and then minus 214 over 3. Okay, so again, all this was just practice trying to get everything expressed as a single power. So again, this was not an equation. There's no x to solve for in here. But going forward, if you want to solve for an exponential equation, we're going to need to be able to express things as a single power. Okay, so right now this is as far as we can take it. Okay, so let's take a look at a few typical type of exponential equations you might have to solve. So here we have 27 to the exponent of 2x minus 1 equals 9 to the exponent of 5x minus 2. So right now there's absolutely nothing I can do to equate the exponents because both sides do not have the same base. So if I want to try and solve this one, I need to be able to express both of these sides, both sides of the equation, underneath the exact same base. So in terms of what base I want to use, you need something that both 27 and 9 are a power of. So something that put to an exponent will give you 9, and something to that different exponent will give you 27. So you can't use 9 as a base because 9 to any power is not 27. However, both 27 and 9 are powers of 3. So I can rewrite 27 as 3 cubed. Okay, and I can rewrite 9 as 3 squared. Because again, my goal here is to have the exact same base on both sides of the equation. I don't have that up here because I have bases of 9 and 27. Now I do. I have bases of 3 on both sides of the equation. So before I can work with the exponents here, actually I'm going to simplify it first, of course. So if I multiply 3 doing power over power, 3 times 2x minus 1, I get 3 to the 6x minus 3. And on the right side, multiplying 2 times 5x minus 2, I get 3 to the 10x minus 4. So again, the reason behind doing this is now I have a single power on both sides. It's the same power of 3 on both sides. Single power on each side, I can equate the exponents. So now this tells me that I can have 6x minus 3 equals 10x minus 4. And once we get down to that step, this becomes a much, much easier problem. We just got to get to that point. So this becomes something you would have solved back in grade 9. So if you solve this, you're going to get 4x over here and 1 over here, so you get x equals 1 over 4. Okay, so and again, I needed both sides with a single power under the same base. Okay, so looking at B, problem here is I have 16, I have 9, I have 55. Again, I can't express all those as the same power right now, but I also don't have single powers on each side, right? I have this minus 9 sticking around here. So the first thing I'm going to want to do is move everything as much as I can over the other side, so add 9 to both sides of the equation. So I'm going to be left with the 16 to the 2x minus 3 on the left side, and 64 on the right side. So I want to be able to express 16 and 64 under a common base. And I actually have two options here. So 16 and 64 are both powers of 4. They're also both powers of 2. I'm going to try and work with the largest base possible, because I express these both as powers of 4. But if you want to use 2, that's absolutely fine. So if I were to express 16 as a power of 4, 16 would be equal to 4 squared. So I'd have 4 squared to the 2x minus 3. And 64 would be 4 cubed, or 4 to the power 3. So once I have that, again, I'm close to being able to equate the exponents. Just got to simplify both sides of the equation first. So I'm going to wind up with, on this side, using power over power, 4 to the 4x minus 6 equals 4 cubed. So I wind up, now again, single power on both sides of the equation. I can equate the exponents. So I get 4x minus 6 equals 3, which tells me 4x equals 9, and x is then 9/4, or 9 quarters. Okay, so that's looking at a few different of the more basic types of exponential equations you might have to solve. We'll take a look at a few more complicated ones, such as this one in part 2 of the video.